Welcome to the Explainer, Class 10. Okay, I know, this is a huge one. You're gearing up for your board exams, and you've hit what is arguably one of the most notoriously tricky chapters in the entire physics syllabus: light, reflection, and refraction. But seriously, don't worry. We're going to break it all down, make it super intuitive, and get you absolutely exam ready. Think of this as your elite physics masterclass. Let's get into it.
Right off the bat, before we even talk about how light bounces and bends, let's just take a second to appreciate what it is we're actually dealing with. 3 times 10 to the power of 8 meters per second. Just think about that. That's 300 million meters in a single second. Light isn't just sitting there, it's this incredibly fast, active traveler, zipping through a vacuum to bring information to our eyes so we can, actually see the universe.
So here's our game plan for today. First up, bouncing light with spherical mirrors. Second, bending light with spherical lenses. Third, we're mastering the ray diagrams. And finally, formulas, signs, and math.
Okay, let's dive into part 1, bouncing light, spherical mirrors.
So what actually happens when our incredibly fast traveler hits a roadblock and has to bounce back? Well, the incident ray comes in, hits the flat surface, and the reflected ray bounces right off. And if you draw an imaginary dashed line straight down the middle, perfectly perpendicular to the surface, that's what we call the normal. The absolute golden rule here: the angle of incidence, or I, always exactly equals the angle of reflection, R. Plus, the incident ray, reflected ray, and that normal line all live in the exact same plane. Pretty simple, right? But what happens when the mirror isn't flat?
Enter spherical mirrors. Imagine a really shiny stainless steel spoon. If you look at the inside of the spoon, the part that actually holds your cereal, it's curved inwards. That's a concave mirror. We call it a converging mirror because it literally forces light rays to meet together. Now flip that spoon over. The backside, curved outwards, is a convex mirror. This one is a diverging mirror because it scatters or spreads the light rays apart. The easiest trick to remember: concave literally caves in.
Moving right along to section 2, bending light, spherical lenses.
So we've seen light bounce, but what happens when it enters new transparent terrain, like a solid block of glass or a pool of water, and actually bends? Well, interestingly, lenses do the exact opposite of mirrors when you look at their physical shape and function. A convex lens is thick in the middle, but here it acts as a converging lens, bringing the rays together. On the flip side, a concave lens is thinner in the middle, and it diverges light. You'll also notice a point O right in the dead center of both. That's the optical center. And that straight horizontal line running right through it, that's your principal axis. Now, just like reflection, this bending, which we call refraction, has strict rules. First, the incident ray, the refracted ray, and the normal all lie in the same plane. Nothing new there. But the real star of the show here is Snell's law. It states that the ratio of the sine of the angle of incidence to the sine of the angle of refraction is completely constant for any given pair of media. We call this constant the refractive index. It basically tells us how much the light hits the brakes and bends when it enters that new medium.
All right, let's tackle section 3, mastering the ray diagrams.
I know. These can look like a terrifying, tangled jumble of lines in a textbook, but I promise you, we are going to completely remove the intimidation factor right now. Just think of these as the golden rules of how light behaves. Every single ray has its own mini narrative. Rule 1. If a light ray travels parallel to the principal axis, it will always seek out the principal focus, F, after it bends through the lens, always. Rule 2. If a ray is aiming right at the optical center, O, it doesn't bend at all. It just bulldozes straight through, totally undeviated. If you can remember those two paths, you can draw literally any lens diagram. Seriously, let's prove it.
Here we go! Case 1 for a convex lens. Let's say our object is incredibly far away, like out at infinity. The light rays are coming in perfectly parallel to the axis. Following our first golden rule, where do they have to go? Right through the focus, F2. They converge perfectly. And because the light rays actually meet up on the other side, the image is real, it's inverted, and it's highly diminished. We're talking essentially just a tiny, tiny point.
Now watch what happens as things move. The object is walking closer to the lens now, sitting just beyond 2f1. Think about our two golden rays doing their jobs. One goes parallel and cuts through the focus. The other goes straight through the optical center O. Boom! They intersect on the other side between f2 and 2f2. So what's the takeaway? As the object moves closer to the lens on the left, the real inverted image gets pushed further away to the right, and it actually starts getting a little bit bigger. Okay, pause. Pay very, very close attention to this one. Examiners absolutely love this special case. Let's say we move the object super close to the lens, right between the focus f1 and the optical center O. We trace our two rays, but wait a second, they're spreading apart on the other side. They are never going to meet. Actual convergence completely fails here. But our brain does this cool trick where it extends those lines backward to see where they came from. They appear to meet way behind the object, creating an image that is virtual, erect, and highly magnified. Fun fact, this is exactly how a simple magnifying glass works.
Whew! After that little brain workout, here's some sweet, sweet relief. The concave lens is literally the easiest thing you're going to learn today. It genuinely does not matter where you place the object on the principal axis. Because it's a diverging lens, the rays spread out and always just appear to meet backward on the same side as the object. So the image will always, and I mean always, be virtual, erect, and highly diminished. Just free points on the exam for sure.
Finally, Section 4, Formulas, Signs, and Math.
Okay, it's time to translate that physical journey of light we just watched into the beautiful language of physics, math. To do this without messing up, we need a map. This is called the New Cartesian Sign Convention. Sounds super fancy, but seriously, if you know basic x and y graphing from middle school algebra, you already know this. Just think of the pole of the mirror, or the optical center of the lens, as your origin, your 0, 0 mark.
Let's just blast through this checklist. The origin is 0, 0. Light always comes in from the left side, always. So any distance measured to the left, basically swimming against the light, is negative. Anything to the right, flowing with the light, is positive. Anything pointing up above the axis is positive, and pointing down is negative. And here's a massive tip. Because we always place the object on the left side of the mirror or lens, the object distance u is almost universally negative. Keep that locked in your mind for when you're doing calculations.
Now for the absolute heavy hitters. The formulas linking object distance u, image distance v, and focal length f. Notice the difference here. It's subtle but huge. The mirror formula is 1 over v plus 1 over u equals 1 over f. But the lens formula is 1 over v minus 1 over u equals 1 over f. The ultimate trick to memorizing these for the boards? It all comes down to a single mathematical sign right in the middle. Mirrors use a plus, lenses use a minus. Just don't mix them up.
Next up is magnification, represented by the letter m. It is simply the ratio of the height of the image to the height of the object. So the crucial point here is understanding exactly what the sign of m is trying to tell you. If m is a negative number, it means the image is pointing downward below the axis, which means it has to be real and inverted. If m is positive, the image is standing upright, making it virtual and erect. Honestly, it's a brilliant cheat code to double-check if your math actually matches the ray diagrams you drew.
We are wrapping up the math section with an incredibly high-yield exam topic, the power of a lens. Power, or P, is just 1 divided by the focal length, f. The SI unit for this is the diopter, represented by a big capital D. But listen, here is the massive trap that catches students every single year. To get diopters, your focal length absolutely must be converted into meters first. If a word problem hands it to you in centimeters, you have to convert it, or your answer is going to be completely wrong. Don't fall for it.
All right, we've covered the speed, the bounces, the bends, the diagrams, and the math. Now it's your turn to apply it. Look around your room right now. What types of spherical mirrors or lenses are hiding in plain sight? Is your bathroom mirror just perfectly flat, or is there a concave shaving mirror nearby? What about the lenses in your eyeglasses or even inside your phone's camera? Take this new X-ray vision of physics out into the real world. Keep practicing those ray diagrams, definitely watch out for those negative signs in your math, and I wish you massive, massive success on your Class 10 board exams. You've totally got this.